why is the inverse BWT algorithm that I've shown you before the break correct? Why is that recovering the original text from the Burrows-Wheeler-Transform? Let's look at what happens, or let's look at how we would do this not knowing this elegant and simple procedure. Let's try to decode the text from the BWT character by character. The first observation is there's a unique occurrence in the BWT of this end of word character $. So we can always find this, and we can always find, in this example here, our favorite banana band, there's the $. Here. So we can always find the row in the BWT, or the row in this matrix where we have to start. That's good. What we have to do now is somehow get to the next character, which means we're currently sitting in a row, but we're not actually interested in outputting this $. We're interested in outputting this character B that's in the same row but at the beginning. The problem is the BWT doesn't directly tell us what this character is, but we can still recover it from the BWT. So that's the first step. We have to find, given a current index in this matrix, we have to find the first character in that row. And the second step is we have to find the next row to jump to, and that means we have to go from the $, back here, to the B, which we'll have to find, but once we've found it, we have to find the B, but we have to find the right row where this B occurs again in the BWT, so that we can continue with the same step walking backwards. How can we do this? Let's look at these two parts in isolation. The first step is you're sitting in a certain row. You're sitting in row I, and you'd like to know the character in the first column. We know that the first column here, that's always sorted. If you look at these characters, by definition, this matrix was sorted. So those characters are the characters of the text in sorted order. The characters of the text is the same as the characters of the BWT. It just scrambles the letters around. So we can take the letters that we find in the BWT and just sort them. If we do that, we can recover this first column of this matrix of sorted cyclic shifts. We can also find the position of our $, that's just the current row. So we can find in the sorted column the ith character, and that happens to be a B. So we know the first character of the text is a B. That solves this Roman 1, the step how to get the first column of the current row. Now the next step is to find the row that has the same copy and that has this B in the BWT. And for that, we come to these arrows. So let's suppose we have decoded a little bit more. Say we have decoded the next A. Then the task is to find the occurrence of the A that we just found in the BWT. And here the important observation is if you have 4 A's, like in this example, and they appear in this order in the text, well, I mean, if you sort the characters, these A's are all the same. But they are occurrences of A in the text, or they represent suffixes of the text. And so I can speak of the lexicographically first A. That's the A at the beginning of the suffix A ban. The second A in sorted order is the one that's, well, this is the last one, that's just N. The third one is the N-band first letter, and the last one is actually our A that we just decoded. So we're in this position now. And so the statement that I just made is that this last A is also mapped to the last A in the BWT. And you can see that this is true. It's the A that comes directly after the B. It's the second character in the string. And that used to be the case here, and it's still the case here. So this is the same A. But why is it necessarily keeping the same order if I go from the occurrences of A to their matching occurrences in the BWT? Why can't these lines cross? And the reason for that is that these are sorted suffixes. These suffixes are in sorted order. So I take these suffixes. Oh, I should have taken the dollar. So we have these four suffixes. They're sorted by definition. Now I take away the first character, which is the same. Now the result is still sorted. And that's the reason why they appear in the same order. So let me copy this, because I think that's the essential part of this slide. Okay, things got a little out of columns here, but it doesn't matter that much. So this was sorted, and now you find the same suffixes with one character less again in this list of suffixes, and those are just the ones where you leave out the first character. And of course these have to be in the same relative order, because they were sorted before, they started with the same character, so this is still sorted. That's the reason. One thing that can happen, as you can see in this example, is the green suffixes were adjacent. They started with the same character. They were a block of exactly all the suffixes starting with an A. Once I strip away the first character, they will still appear in the same relative order, but there could be other suffixes that are inserted between those. Like in this case, the banana band comes between the first and second of the blue suffixes. But that's how we can solve this second part. So to wrap this up again, whenever I take the occurrence of a letter, so this is not just a character, it's also a position in the text, and that makes this A unique. There's a first A in lexicographic order, which happens to be the third A in text order. The third A in text order is, again, this first A in lexicographic order in the BWT that becomes the first position in the BWT that is a 1, that is an A. So first character here, first character here, second, second, and so on. So that means if I have the row where I have a character in the first column, I can find the corresponding column in the BWT by going to the appropriate character in the BWT. If I'm looking at the second A in the first column, it is mapped to the second A in the last column. And if you look at how you do this sorting, this is exactly how you do how you create these next pointers. You you sort things by the first character. That generates the list sorted according to the first column. But then you keep this R open. So you keep this index in the BWT intact, so that even after you shuffled this around, the relative order of all the A's is still the same. Those two things taken together is what happens inside this inverse BWT procedure. The following these list pointers is exactly following these red pointers. And one more time, what's really going on is you start in the row of the dollar, you jump to the first column in that row, and that gives you the character you have to output, and then you map this occurrence of the character to the appropriate occurrence in the BWT. All right, so maybe a last time, let's go through this example. We start in the column with the dollar. We map it to the first. That's just finding the character. So the dollar is in position 6, 0, 1, 2, 6. So we find in the sorted list of characters, we find the 6th character, that's a B. So we find that T starts with a B. We also see in the list of sorted characters that this is the second B that I find. So I map this to the second B in the BWT, that's this. So we're now in row 4. And again, we can look in the sorted list, what is the character at index 4? That's an A. So I output this A. It's not just any A, it's actually the last A in the sorted order. So I map it to the last A in the BWT. So we're now in this position, in this row, row number 9. Well, we find the character at that position is an N, and it's actually the last N in sorted order. So we map this to the last N in the BWT. There we are. So we are now in position 3. We find the thing at that position is an A, and it's actually the third A. So we go to the 1, 2, 3, third A. Jump to the beginning, that's an N. It's the middle N, the second, so I go to this position. There I find an A again. That's the first A, so now I go to this position, position 5, then there I find a B. This B is the first B, so it takes me to this row. There I find another A. That's the second A, so I map it to the second A. It's down here. So I find the N. And now the N is the first N, so that takes me to the first row, and I find the dollar. And that's the sign that I've completely decompressed this thing. I hope the second example might have made this more clear. I really try to make you understand how this works. Try to remember maybe more this picture than the actual algorithm from the last slide, but of course that algorithm is faster to execute. That's pretty much all I want to say about the BWT. I have one bigger example that I want to discuss with you, but let's first talk about the properties of the BWT again. The running time for both encoding and decoding is linear in the size of the text. However, encoding is slightly more expensive because it uses suffix sorting. And we spent the better part of chapter 6 to prove that we can actually sort suffixes in linear time. That was one of the most complicated algorithms in the whole class. Decoding, by contrast, just has to sort by a single character, and that's it. The second part is following this linked list, jumping through this array. That's fairly simple and fast. So decoding is much easier, but in the course notation of a theta class, the two are the same. The downsides of BWT is that it is typically slower than the older compression methods, and it definitely needs access to the entire text. You can break the text into blocks, but that then makes the compression a little worse. So this is definitely a downside. But the positive part is that this pipeline, BWT, which is the most important part of this pipeline, followed by move to front, run length encoding, and Huffman encoding of the outcome, that tends to have the best compression of any method known for natural language text. And I think this is still the state of the art, which is pretty impressive. In other fields, the best practical methods tend to get complicated, or well, at least need tweaks and twists. And here for compressing text, this clean and elegant method seems to beat even attempts like 7-zip that try to combine many different methods and pick the best of them. I'd like to look at one example in a little more detail. So I'll open the question in a second, but this is really something to think about. It's a little deeper than the usual Pingo questions, so maybe it's worth spending a little more time on this too. And it's, again, discussing the essence of what makes the BWT helpful for compression. So we have a text that is somewhat repetitive. It contains a lot of different forms of half. And I already computed the BWT for you. Now you might notice that indeed the BWT looks fairly non-random. It has many runs of characters, of this repeated characters next to each other, which is not something that random text has, but I had to make a fairly long example for this to really show. You get a similar behavior for proper English text, not this made-up example, but just by the fact that there's a limited vocabulary that we usually use in natural language. So you get a similar effect as in this artificial example, but to make it fit on the slide, I kept it to this length and made it, well, it's not a proper English sentence really, I think, but explains the point. So I want you to focus particularly on this run of H characters. And I'd like you to think about what this run of H's means and how you can explain that the BWT contains this run. So I'll now head over to Pingo and start this question. I'll give you maybe 2 more minutes because we're heading towards the end of the session. There you go. I did see the question that one of you sent on Slido, but I guess it was a test question and you withdrew it. If you do have questions, feel free to post them there at any point. I hope I can see them with no delay. And either way, I would discuss that at a time where it fits into the lecture. So that's not the current question. Here it is. I'll go over to the slides for a few more seconds. So I can answer that question. Yes, we still use the Pingo username sign-in. I take it as a sign that you arrived a bit late, because I did start it at the beginning, but only for the first so and so many minutes. I can open it after we've finished. All right, so there seems to be a majority for option D, which is H is always followed by an A, which is not wrong, but I would say slightly more correct is this option, that all A's are preceded by an H. Now this is, I mean, okay, this is not far off, and many of you ticked this, and I said this is a tougher question than most of the Pingo questions. To explain why this is maybe slightly more on topic, I put here the matrix of sorted cyclic shifts. So here, this is all sorted, this is all cyclic shifts non-sorted, and here are they again in sorted order. So what we're looking at is this run of H's here. And what we should do is really look in the same rows, but at the beginning, what happens here. And you see that there's a lot of A's. So this run here happens because after the H, there is an A. So all these H's here were brought together because they are followed by an A. We could have had more characters in this. So these are all the occurrences of A's. It could have happened that there was another character inserted into here between those, splitting this run of H's into two, if there had been another character that precedes A at some position. Say we would have, I don't know, we could have had this, or maybe to make it a little more interesting, we could have had this word in our list. If we look at the suffix starting at this A, it would have fit somewhere in between here. So this was, of course, not planned, but I almost got it correct. So it would, in between these two, we would have seen a T. The fact that we do not have a T here is not because H is always followed by an A. That would have been true in this list too, but it's more that all A's are preceded by an H. So there's no other character like this T that also precedes A and which would also be inserted somewhere here in this list. That's the precise reason why we see this run of H's here. The other reason, the other answer, this is definitely not far off. And to some extent, also the first and second answer can be made sense of, even though they're not exactly correct in this at this point. You could explain with the first and second answer, you could talk about this run of space characters here, or underscores. Okay, we're nearing the end of today's slot, so I'll wrap this up. Just what I wanted to show on this bigger example also is, here's the BWT again, and if you apply the move to front heuristic, you get this sequence of numbers. Now this looks long, but it's actually good. It's actually very compressible, because on one hand we see lots of runs of zeros. Those are the original runs in the BWT. But also if you look at the other characters, we see a lots of 8s, 5s, 8s and 9s, but we don't see a lot of other numbers. And that's kind of non-obvious. Why would the move to front heuristic not find other numbers? That's one of the other reasons why this particular pipeline compresses text so well. All right, that brings me to the summary of this whole compression chapter that we started a long time ago. Just to remind you a little bit and give you something for reference, we discussed essentially these 5 algorithms or encoding techniques. We were talking about Huffman codes, which give, it's an alphabet encoding, a character encoding. It assigns one code to each character, and those codes can be of variable length. And we actually could show a precise, rigorously proven optimality result for Huffman codes. Then we were looking at run length encoding, which is one of the more interesting ones. It has the feature that it can compress very repetitive bit strings with lots of long runs very, very much. It can compress them very much down. But it's in isolation not very effective. Then we were looking at Lemplisiff-Welch, which was building this dictionary by adding new phrases all the time. This is again something that's very effective for natural language text and has the feature that you can apply it as a streaming algorithm, doing it, reading character by character and compressing character by character almost. And then there were the 2 transformations that made a text more compressible than it otherwise seemed, to specifically these 2 methods. And that's move to front, where we kept this move to front list of alphabet characters and thereby could turn certain patterns into runs or skewed distributions over the characters. And finally, the BWT, which, as you've just seen, can exploit repetitions in a text even if they're very far apart from each other. It still groups them together and exploits the shared context. That's the end of the compression chapter. I hope you enjoyed this. This is one of the, as I said before, it's one of the topics where you can get to the forefront of the best techniques we currently have with limited effort. So it took us 2 or 3 weeks to digest this with a little bit of preparation from chapter 6. But you have a very solid basis now for these compression methods. And that's what I like about this chapter very much.